Hello, and welcome to another video on machine learning and biotechnology. I'm Ian Hoffecker, and this video is going to be about the topic of linear regression. So first, I'm going to start with a bit of review, talk about probabilistic models and optimization, which we've covered in previous videos. And I'm going to talk about linear regression, which you're probably familiar with already, but might not be familiar with as a maximum likelihood estimation problem. So we're going to talk about that. And then we're going to talk about how it's actually done in practice using the least squares estimation method, or LSE. And then we're going to start talking about dealing with multiple variables, multivariate data sets, and also the general pipeline of going from data to model to prediction. And one of the steps in these supervised machine learning problems, which is that of creating training and test data sets or data partitioning. And then we have an exercise where we'll look at these topics in more detail. So first, some review. In the previous videos, we've covered this idea of probabilistic models and how we can take a piece of data or a set of data and explain it and predict its distribution through the application of a probabilistic model of some kind. And so previously we looked at an example which was that of restriction enzyme cut events and counting them. And we had this variable k trials to get to a certain number of cut events. And we had this data set that was generated by us simulating this process. And then we hypothesized later that we could also explain this data using the negative binomial distribution function, or the Pascal distribution function, which had this format. So this is a likelihood expression. And the idea here is that we're interested in knowing the probability of a particular output variable, or the variable that we're interested in modeling. So in this case, that was the number of trials k, given certain values, a certain set of parameter values, R and P. And then we had this analytical expression which accepted these values and then would spit out a probability. And this was called the likelihood. And basically, we're interested in maximizing this value. So we want to maximize the probability that we would have seen this particular data given a certain set of parameters. And what are those parameters? So the way we could do this is by scoring the result. So the likelihood function is itself kind of score, but what we could do is formulate this as a negative log likelihood, and then this would become a cost function or a loss function whose minimum the machine could find for us. So rather than tweaking these parameters manually, adjusting the values, which we could do, the machine would do this at a much higher rate, and then hopefully deliver us a global minimum value for this loss function, as well as the corresponding parameters that it used to find that global minimum. And this format of a likelihood expression, a probabilistic model here, we're going to see again and again. And so another embodiment of this was in the case of the Gaussian mixture model, which we said was a technique that we could actually use to cluster data, unstructured data. And in this case, we had a similar expression. So we're interested again in this probability expression given a certain set of parameters. But instead, the model in this case is represented by this summation of multiple Gaussian distribution functions, each weighted by some factor pi here. And what we would do is just the exact same thing. We would do the exact same thing that we did in the Pascal distribution case. We would take the negative log of this, sum this up for all of the data points that we have in our data set, and this would return us a good fit, an optimal fit for this observed distribution here and the set of parameters that correspond to it. And this gave us not only a way to kind of produce a nice smooth fit to this distribution, but it also produced an underlying explanation for what we were seeing. So we said, there are three Gaussian distributions underlying this mixed distribution here. And we could see that, okay, these data points here correspond to this distribution, and these data points here correspond to these overlapping distributions here. And for performing this minimization step here, we talked briefly about the algorithms that are used. So these are typically gradient descent optimization algorithms. And the idea with these was that we have some space that we can imagine might be a high dimensional space that's hard to picture, but in this case, we have a two-dimensional space. And the axes here correspond to values of the parameters, and the contour or the height here corresponds to the value of whatever our loss function is. So in our case, this was typically the negative log likelihood. And the idea was that we're trying to find the lowest point in this space. And the way we do this is by a kind of blind walk where we're sampling the local values of the negative log likelihood, changing the parameters in various directions, and then just looking at the direction in which the negative log likelihood is changing the fastest and tweak those parameters in just such a way that we go down this slope towards our goal as fast as possible, as efficiently as possible. And so this was a bit of an art. We kind of discussed how there's all these things to think about: the learning rate, the step size, how adaptive you are, how you can get into trouble trying to find the global minimum, and that there might also not be just one global minimum, but there might be multiple local minima that you could potentially get trapped in, and this would make your optimization harder. So that was gradient descent, and this is, of course, going to be a common tool that we use in a lot of machine learning applications, but you might already be familiar with it in the context of the Excel line fit. So if you've ever created a scatter plot in a spreadsheet and fit a simple line to that data, then you have experienced some kind of gradient descent, most likely, or optimization, most likely. And this is going to be the topic of today. We're going to focus on linear regression, which is the underlying process used to fit these lines. And we're going to go a bit deeper into it than you might potentially be familiar with. So what we're usually working with, right, is we have some scatter data, and we're interested in finding the equation of the line that best fits that data. And this equation would usually have the form y is equal to some intercept, so some point where the line is intercepting the y-axis, and plus the x variable horizontal axis times some slope. And we're going to use this notation, these w's here, because of the machine learning convention. So we'll typically call this intercept a bias, or the starting value of our predicted variable here. And this w sub 1 here, we will refer to as a weight, or in other words, how much the input variable x matters in how much it contributes to the value of the output variable y in this case. So essentially the same thing that we're used to, y equals mx plus b, but here we're just kind of changing the names a bit to fit the machine learning conventions. But the other thing we can do is look at this from a new perspective, which is that of a probabilistic modeling perspective, right? So we're not just dealing with a line here, we're dealing with the distribution of points around this line. And so we're, of course, not expecting those points to fall exactly along this line. We're expecting them to be hopefully uniformly, or at least symmetrically, distributed around this line, with most of them appearing kind of close to it, and hopefully not too many that are really far away from this line. And so actually what we've just described here is a kind of probability distribution, one which depends on the x value as one of its parameters or inputs. So we can create a likelihood expression just like we did for the Gaussian mixture model or the Pascal distribution, which is going to describe the probability of observing our data given a certain set of parameters, one of which happens to be the x value here. So instead of x given theta, we're looking at y given x and theta here. And then on the right side of this equation, what we have is a Gaussian distribution. And so this might not always be the case. Sometimes noise is distributed according to some specific distribution, but in a lot of cases, we're going to be modeling the noise around fitted line as a Gaussian or normal distribution. So if you remember, we use this fancy n here to denote the Gaussian PDF. And here the parameters for this Gaussian PDF are, as usual, the mean and the variance here, or standard deviation, sigma. But in this case, the mean here is changing. So we don't have just a single fixed mean deciding where our Gaussian is centered. Our Gaussian can be centered at any number of locations depending on x. And so what actually goes in here in place of mu, a single value, is going to be our line equation. So y equals mx plus b, or the bias plus the weight times the x value. And then that then is going to complete the variables that we need to have to predict the distribution of y variables around that. So it's going to be normally distributed about this line if we've found the optimal set of parameters, that is. So how do we find those optimal set of parameters? So we could do this, in fact, just like how we've done the other maximum likelihood estimation problems. So this is a likelihood model, probabilistic model, and we can reformulate it as a cost or loss function that is to be minimized. And again, we simply do that by taking the negative log of it and summing up those values for all of the data points, all of the x values in our data set. And we will then throw this into a minimizer, and that minimizer is going to hopefully return values of the weights and biases, W0 and W1 here, as well as the variance, how the spread of the distribution is. So, and then to just picture this, imagine we have an x point here, and we're looking at a particular data point, and we're interested in this question. Given our set of parameters, we've got a line going through here. We've fitted these weights accordingly to predict this line. What is the probability actually that this point here has the y value that it has at this x value? And hopefully, if we've done this right, these values will all be pretty high. But if we get one, way up here, then we're going to have a very low likelihood associated with that point. And so this becomes the basis for obtaining a good fit for a line. What about multiple variables? So this starts to get very hard to picture, but we can do it for two input variables. So now instead of x and y, we have x1, x2, and y. So y is still our single predicted outcome variable, but now we actually have two input variables, x1 and x2. And each of those are going to have an associated weight with them, how much that variable matters in determining the output y value. And we're once again going to have a single bias value, which is going to be the starting value, you can imagine, of y, how much we're shifting all of our predictions up in the y axis, on the y direction. And so geometrically, visually speaking, this is the equivalent of fitting a plane to a scatter of data. So if you imagine, I tried to draw these dots with some perspective here. So these bigger dots are closer to you in space. And then these smaller dots are, you can imagine, farther away from our viewpoint here. And we've got these two axes here, and we could pick a particular point set of x1 and x2 values, and our model then is going to spit out a single y value that's predicted for those two sets of inputs, given at least our model. So the model here, or the plane here, is going to be determined by the weights that we have going on up here. Okay, how about for three variables? Okay, this becomes quite difficult to draw and sort of impossible actually to visualize. But if we can imagine, now we have three input variables all perpendicular to each other in the same way that these variables are perpendicular to each other, which of course does not work in a regular 3D universe that we live in, but we can kind of try to use our imagination a bit and again say that we have 3 points here, or 3 values, x1, x2, and x3, and a particular point associated with those that gives us a single output y value associated with that. And then you can imagine you can keep going with this. So we could have 1,000 input variables, x1 through x sub 1,000, and then again, a single outcome variable y. And how does this look as a probabilistic model? So again, we're thinking about this in terms of a Gaussian distribution. So we drew this point, we have these 2 points, or these 2 values, x1, x2. And we said this is going to correspond to a single point y here. That's going to be given by our plane. And this single point, again, is going to form the mean parameter for a Gaussian distribution. So we're once again not expecting all the points to lie within this plane, infinitely thin. Rather, we're expecting them to be Gaussian distributed throughout, above and below this plane. And so where you are in the plane is going to determine where this Gaussian is centered. And you can imagine our probability then of getting a point above or below this particular y value is going to be Gaussian distributed. And we'll have this likelihood expression then, which is going to be the product of several Gaussian functions here. But once again, it's going to have the same format here, where we're having the x value here as one of the inputs along with the variance. So here's kind of visualization of what it might look like. So we're got this scatter, and now imagine we're systematically adjusting the parameters, the weights and the biases, in order to minimize a loss function. And that loss function could be the negative log likelihood, for example. And we're trying to find the place where the gradient of that negative log likelihood function is zero also, so the place where it's no longer changing. And that's happening by the process of gradient descent. Computer is looking locally how the loss function is changing and trying to take steps that maximize the rate of that change until it's changing no longer. And then that corresponds to optimal point. And that optimal point then is going to give us the final fitted line here. And here is just a visualization for 2D case x1, x2. Here we've got a scatter throughout that space, and we've fitted a plane to it, which we've just drawn with this triangle here, but you can imagine this plane is extending in all directions past the boundaries of the plane. Okay, so that's a familiar idea, but what if I told you that we could also use linear regression to fit nonlinear functions? So isn't this a bit of a contradiction? So this is actually, you can, I believe also can do this in Excel. For example, fit a polynomial. So this is a function which has an x squared term in it. And this is still happening by linear regression. So how does that work? Well, it works exactly the same way. We're going to use gradient descent. We're using these weights now. So we have 2 weights. And what's linear is actually the relationship between these terms here. And so this is what we're referring to when we call it linear regression, because we have terms that are used to predict y, our outcome variable, that are added together. And because they're added together, that means they're linear in the parameters, in terms of the parameters, even if the input variable happens to be some function, x squared or square root of x or something like that. And this is still going to give us a fit that could work here. And that's maximum likelihood estimation. And maximum likelihood estimation is depending on this gradient descent algorithm, which is an iterative, kind of computationally demanding, often process with issues sometimes like local minima. So wouldn't it be nice if there were a non-iterative way to locate the maximum likelihood estimate? And in fact, there is, at least for cases when the noise around the line is Gaussian distributed. And so in the vast majority of cases, people are going to be using something called the least squares estimation method. And the idea is that you're trying to find the minimum of this quantity here, the residual sum of squares. And the idea here is that it's the sum of these quantities, these squared quantities. So y minus the data y here minus the predicted y. And here we're just showing the weights and not the biases. Why is it squared? So this is to make it absolute, right? So we don't want values above the axis to cancel out values below, not the axis, the line. And to do that, we can square these quantities, so making negative and positive the same. So if you're far away from the line, you're going to have a bigger value than if you're close to the line. And then these two values, data and predicted, are going to be closer together, and this quantity will be smaller or closer to zero. But regardless, it's going to be a positive number when you square it. So by minimizing this value, we're essentially finding the point where we've minimized the lengths of these distances away from our fitted line. So why is this attractive relative to maximum likelihood estimation? So this is kind of similar to what we said at the end of the Gaussian mixture model episode, where we said that in practice, you have computational cost of doing maximum likelihood estimation. It's good to think of it in terms of this probabilistic mindset, but in practice, it's done using a more efficient algorithm for navigating this loss function. And this is exactly the same case here. So this turns out to be a much easier problem than the probabilistic model. And it has an analytical solution. So the gradient or the rate of change of this function has this expression here, which we can set to 0 at its minimum. So the point where the slope is not changing, which we said earlier corresponds to the optimum or the minimum of this loss function. And it turns out there's a simple analytical solution here, which is this expression. So it's going to be the transpose of the data matrix multiplied by the data matrix, the inverse matrix inverse of that, and then that multiplied with the transpose of the data matrix times, or matrix multiplied with the output vector. And this, in fact, is a single analytical expression. So this can be solved without iteration, without experimentation. This can just be solved. And that will then give you an optimal value for the set of weights. So this is just a kind of reminder of what these ideas are. So matrix multiplication is this process here, right? Where you have, say, an m by n matrix, and then you're allowed to multiply it with an n by m matrix. And the transpose is when you're switching the rows with the columns. So the rows become the columns become the rows. So if it's m by n, then the transpose is going to be n by m. And then what you're doing is multiplying, pairwise multiplying the row here with the column and summing up those pairwise multiplied quantities to form the entry for the resulting n by n matrix. And then the matrix inverse is this problem here where you've got a matrix and you're multiplying it with some other matrix, the inverse, and that multiplication should result in the identity matrix, which is the matrix which has diagonal ones like this. So this is the matrix inverse, the one that gives you this identity matrix here. So this is how these are done in theory, but in practice, we're going to use the computer to do these. So I've made a little guide here, one for Python on the left here and one for R. And so this is going to show you the commands that we would need to enter to perform, for example, a matrix multiplication, the dot product here, between two matrices, or a matrix and a vector, and to compute the transpose as well, or to compute the inverse. So we have this for both here. And this is in Python, this is going to be utilizing the NumPy numerical Python library. And in R here, we're going to be utilizing this mass library. So this is going to be useful for us completing our exercise. So I'm going to give a little introduction here to the problem that we're working on. So the idea is we have a big data set here of gene expression profiles for various individuals. So you can imagine the rows here correspond to different individuals, and these numbers correspond to the transcripts per million for particular genes. And we have a set of 400 different genes here, ending with gene 399. And each of these patients have different levels for these different genes. And they also have a measured blood sugar level. So this is a kind of simulation of a diabetes study. And what we're interested in is if these patients develop later on in life diabetes. So here we have this pathogenic label. And so this data set is, what I've done here is, so it's an artificial data set. And what I've done is I've buried some structure in this data that we're going to be exploring over the next 3 lectures, including today. And so today's exercise is to just explore this data set using linear regression But then next week and the week after, we'll look at it with other tools, such as neural networks, to explore some of the data that will not be revealed today by linear regression. So, but the idea here is to just kind of get started. And the first thing you're going to do is visualize the data set here. So we can print out the matrix, and we have all 3,000 individuals here on the horizontal axis, and all of the genes listed here on the vertical axis, and the darkness here is indicating the relative expression levels for each of these genes for each of these individuals. And then the other thing that you'll print out when you run first couple cells is this histogram here of blood sugar levels. So each of these patients is associated with a blood sugar level. And the way blood sugar works is you typically have a normal blood sugar if you're in this neighborhood here around 80, 70. And then if you're up above the 100, 120 range, you're pre-diabetic. And if you're in 130, 140, then this is diabetic level. And the colors here are indicating this pathogenic label, or the proportion of individuals in this bar here at this point who later on in life developed the pathogenic diabetes. So it's quite red here. So we can imagine maybe this is like a high risk population that we're interested in. And then those who had lower blood sugar levels here, we're expecting them to be less likely to develop diabetes later in life. The problem here is to first complete this normal equation function. So this is the equation that's solved over here for computing the fit for the least squares estimation method, or getting our linear regression parameterized. So it's this equation here, x transpose dotted with x, inverse of that, times dotted with x transpose dotted with y vector. And so that's the first task, is to complete this normal equation function, and specifically this line here. And here we have the Python starter and the R starter. And once again, just kind of summarizing the reasons we're doing least squares estimation. So it's a analytical solution, doesn't require iteration, and it is in fact equivalent to solving the maximum likelihood estimation in the case when the noise is actually a normal distribution or it's symmetric. In contrast to that, you have maximum likelihood estimation, which is perfectly viable, but it's going to be more computationally demanding. But an advantage to it might be that it's more generalizable. And so you could, for example, use a different distribution to describe your noise. Maybe it's not symmetric, and this would be a more accurate way then to perform a fit if that were the situation. And then the other task that we're going to look at here in this exercise is to get some experience with the train and test workflow or pipeline that's going to be quite typical with a lot of machine learning problems. So the idea here is we have an input data set and an output data set. And so this is supervised machine learning, right? Where we want to train our model, get some parameters, and then test our predictions. And often the best way to test your predictions is to reserve a subset of your data that will not be used in the parameterization. And then that will be used to test your predictions. So we could take the inputs of this test data set and produce predictions, and then compare those with the actual predictions that we have access to in this data set. And if our model is trained well, then these will be hopefully very similar. What you can do is shuffle this partitioning. So we could take a different subset of the training data and a different subset of the test data, and we could repeat this process multiple times and just get an idea of how robust our training algorithm is, how often we're able to get good predictions of y, or how sensitive it is to changes in the input or the training data. So this is to avoid things like overfitting, right? So we could, if we were to take just a few samples and train our model, we would still get something, but that something might not actually be able to predict the right values because it's actually partly been parameterized by some of the noise inherent in the training data. And so this process of splitting into different sets and shuffling around and doing this is known as cross-validation. And so this is the second thing here. So we have in the exercise, we've set up the pipeline here. So we have our X input here, our Y output here. And what we want to do is have two X's, one for training, one for testing, and two Y's, one for training, one for testing. And your task here will be to complete this line here. And you'll utilize this function train test split if you're doing Python, or this create data partition if you're in R. And to give you some help here, I would recommend Googling this or looking at the documentation. So this train test split comes from this sklearn, scikit-learn library from Python, or the caret library in the case of R. And then you can see here, if you read the documentation, what kind of inputs you will need to run this function. And if we did all this, then we should have successfully generated a scatter plot here. And this is not to be confused with the Excel line fit, right? Because this is a multivariate fit. So we have actually hundreds of X variables. What we're plotting instead is the true value, the ground truth blood sugar with our predicted value. And if the linear regression has worked, then this should be correlated relationship here, which we can see is true to some extent. And then you'll see that we also spat out this quantity here, the R squared, which is a value between 0 and 1. And this represents, so this is referred to as the coefficient of determination. And it has this equation here, 1 minus the residual sum squares divided by the total sum squared error here, which is the Y values minus the mean. So this is kind of the average variance in this data set. And this is the variance that is described, the variation in the data that's described by our model. So Y sub I minus Y predicted. And so a value close to 1 means that you're explaining a lot of the variation in the data with the model. And if it's close to 0, then the majority of the variation is unexplained, unaccounted for. And 0.5 would indicate that half of the variation in the data is accounted for by your model. And again, so these come from the definitions of variance statistic. So that's it for this lesson. So we looked at linear regression kind of from a different perspective than maybe you might be familiar with, which is that of a probability distribution perspective, or thinking of it in terms of a probabilistic model that we could perform maximum likelihood estimation on in order to get our parameters. And then we talked about multivariate models, this idea of adding multiple inputs, which can start to get hard to picture in your head. But for example, for 2 inputs, we can picture this plane fitting this data. And what's important about this is realizing that actually linear regression is a pretty powerful tool. So it's much more than just the line fit from Excel. We can handle this kind of complex data like gene expression profiles, for example, and really mine a lot of useful information from it. And then finally, we talked about this pipeline or workflow, which is going to be really common in supervised machine learning tasks, where you're splitting your data into training and test sets. You're obtaining your parameters after some kind of optimization fitting process, and then you're using those parameters then to make predictions, but then also check your performance with your remaining test data. So that's it for this session. I'll see you in the next one. Bye-bye.